This video is going to look at how to create exponential functions and equations from um, looking at charts, perhaps looking at a list of data, reading a written description of a situation, and taking those various situations and turning them into exponential functions. So I'm going to start with a table, such as you see here. And the first thing you got to be able to do is look at a list of numbers or data and determine that it is an exponential situation. So in this one, your x values, really all I'm looking for here is that there's a pattern. So as long as there's a pattern, so I can see that I'm going up by ones each time. So what has to happen if it's exponential is there must also be a pattern down here. Now it can't just be any pattern. To be exponential, what has to happen is you have to be taking this number and multiplying it by some number, and then so times the letter we use, it's called R, common ratio, and then this one has to be multiplied by the same thing again, and then this one has to be multiplied by the same thing again. So something that's really obvious, you can just tell by looking at it, well, look, we're multiplying by 2 or 3 every time. However, sometimes like this one, you may be looking at the data saying, well, I don't know, is it exponential? Is it not an exponential? So what I would do here to see if it's exponential is I would take the second term and divide it by the first term. I'm going to say, well, what's 2.4 divided by 2? Well, that one we can do in our head. It's 1.2. If this data is exponential, when I take this one and divide by this one, I've got to get the same thing. So 2.88, divide that by 2.4, 2.88, divide that by 4. Got my trusty calculator out here. And it also gave me 1.2. If you were to take 3.456, divide it by this number here in front of it, 2.88, you will get the same thing again. I always tell students, usually if you try it 3 times and it works 3 times in a row, you can usually be pretty confident that that you're dealing with some exponential data. That's the first step. Determine whether the data you're dealing with is actually exponential. So in this case, I've determined that it is. So the next thing I'm going to try to get you to figure out is how do you turn that into an exponential function that would give you, let's say, the 20th term in the pattern without us keeping having to multiply by 1.2 over and over until I got to the 20th. Well, if I was going to model this data, we're going to make functions that look like this pattern. Y equals A, B, to the exponent x. So we need to figure out what do I put here, what do I put here, and eventually what are we going to have to do with our exponent? Well, in this one, the A, the number in front here, is always what we call the initial amount, or your starting amount. So in this case, that means in the beginning, so in the beginning, when x was 0, this function started at 2. So that would be, this would be your starting amount, the 2. So if I'm going to create a function here to model this data, y would equal 2 would be your A value. The B value is representative of what we call the common base. Also referred to as the common ratio. Hence the letter R we use up here. That R is there for ratio. It just means what are you multiplying by repeatedly to get from one term to the next in the pattern. So in this case, our common ratio, we identified over here as 1.2. Therefore, I'm going to put a bracket here. There's my base. As long as you're going up in increments of 1, this will always just be the exponent x. Now, we'll deal with what if it's not going up in increments of 1 in a moment. But for now, because it's going up by 1, it's just this. Now you may say, Oh, I wonder if I did this right. Well, we can check it. Let's put in x is 3 and see if we get that number. So if I went y equals 2 onto 1.2 to the exponent 3, type that in your calculator. So 2, oops, I forgot to put my 3 here. So as I was saying, we're just checking it to see if we've, well, let's try this one. Let's put 4, just because that's one we haven't even looked at yet. So we'll put to the exponent 4. So I just substitute 4 in for the x. I go 1.2, raise it, make sure you do order of operations. So 1.2 raised to the exponent 4 multiplied by 2. Now, of course, many of you have calculators. You can just type in exactly like you see here. So put your 2, bracket 1.2 to the exponent 4, hit equals. You will get 4.1472. It works. So we have created a correct function. All right. So let's take a look at a few more of these. And so this would be something too, they refer to it as modeling. You're taking data and you're modeling it with a function. So we're modeling these with exponential functions. So in this one, notice the scale's no longer going up in increments of 1. So what happened here, students will look at this and say, I can clearly see a pattern here this time. I'm multiplying by 3. But the problem is it's not going 0, 1, 2, 3, 4, 5. So that's going to make one little change. If you think about what happened here, to get from 0 to 2, I had to skip 1, which means I multiplied by whatever the common ratio is. That would have got me, imagine there was a term here, 1, and there would have been some number there. But then I would have taken that and multiplied by another r to get to there. So the fact that I've skipped 1 really means that I've multiplied by r twice to get to this term. Now, how does that affect our equation? Well, we're still going to go y equals a b to the x. But here's the key. When you look at this and said, well, I'm multiplying by 3. So it appears in this chart that the common ratio is 3. However, the dilemma is the x scale is not going by 1s. To deal with that, what I want you to realize here is because you multiply by r, in this case, r squared actually equals 3. Now, I know this can start to sound, oh my goodness, it's getting confusing. There's a nice little trick that takes care of all this for you, which I'll get to in a moment. Think about if this had went by 3s. So in 0, 3, 6, 9, 12. That would mean that I multiplied by r 3 times to get to that value, which means that this would have been r cubed equal 3 instead of just r squared equal 3. We want this number to be the common ratio, not the common ratio squared. So in this case, to get the common ratio, I would take the square root of both sides, and r would be the square root of 3. Now here's the little trick. Another way to write square root of 3 is 3 to the exponent 1/2. This is the key. Notice here that the denominator, the 2, coincides with my scale. I mentioned to you, imagine that this had went 0, 3, 6, 9, etc. Well, then this would have been r cubed equaled 3. When I get down here, r would have been the cube root of 3 instead of the square root of 3 because I would have multiplied by r 3 times. Well, then r would have been 3 to the 1/3. Again, the denominator here would have coincided with my scale here. So here's a real nice, easy way to fix. So all of this, again, hopefully you understand why I'm doing this, etc. But here's a nice little trick that fixes everything. You just put y equals a b to the x, and then you just put over c. And the c will now represent our scale on the x-axis. So in this one, this becomes really easy now. So it's y equals a. Remember, a is your starting amount. So when you had nothing at 0, what was the starting amount? So there's my starting amount. The base, what are you multiplying by Don't worry about this whole r squared bit anymore. I kind of explained over here. Just do it like normal. So you say from here to here, I'm multiplying by 3. Here to here, I'm multiplying by 3. That's going to be your base. Now here's how we're going to adjust the base. It's going to be x, but because my scale is going by 2's, my scale is going to be x over 2. And what that does is it really has your 1/2 here now. Remember we said it's really 3 to the 1/2? Well, there is a 1/2 in front of the x, so now the base is really 3 to the 1/2, which we said it would be, to the x, which is now all taken care of here. So again, you can say, oh, I don't know, did I do that right? Let's try 8. So if x is 8, I should get 81. 1, 3 to the exponent, 8 for x over 2. 8 over 2 is 4. 3 to the exponent, 4. 81. It works. Okay, so that's how you build exponential functions from a listing of data. So you've got y equals ab to the x over c. I'm going to have that all organized here. Oh, we got one more. So let's do one more. So I can see here I'm clearly multiplying by 2 each time. That makes it exponential. My scale here is going up by 1/2 each time. Fine. So we're going to go y equals a b to the x over c. We just got to fill in the numbers in the right spot. So y would equal a. What do I start out at? 5. My base, what am I multiplying by to go from term to term? I said this one's fairly obvious, so that's a 2 to the x. Right, that's always just your unknown. And now this will go with your scale here. So it's that. Now, anytime you think about this, there's a 1 in front of the x. So really what I've got is 1 over 1/2. We don't usually like to write fractions within fractions. So this is the same thing as 1 multiplied by the reciprocal. So it's really just that. So this would be another way to write this function. It would just be that. Okay, here is everything summarized for you. So A is your initial amount, and this could be, I've shown you how to do it in a nice listing of data. It's not always going to be presented that way. What I would encourage you to do, even if it's presented in some other way, if you found what I just did reasonably easy once you kind of watch me do a couple of examples, well then set up every question, regardless of the situation, to model that type of a pattern. That's what I'll always do. So you'll see what I mean by that when I start doing some examples here. They're presented in a different fashion. So it says, how do I get the base? Well, it might be given in words. It might talk about something doubling. It might talk about half-life. It might talk about something tripling. It might talk about percentages. We'll have to read the question and figure that out. And we talked about this. This is your increment or your x scale. Could be given in words, in a table, on a graph, whatnot. So you'll see how this all works out. So here's an example. This is just some buzzwords. You'll see double, triple, quadruple, half-life. Kind of that's what your base would be for those. So here's an example of a population. So it says the population of a certain colony of bacteria triples every 2 hours. If there are 1,500 present initially, how many bacteria will be present after 7 hours? Okay, so what I'm going to do is, as I said, I always like to make a little chart. So I'm going to, in this question, rather than x and y, I'm going to use time. And I'll use p for population. So this is like my x and my y. In the beginning, I had 1,500. After 2 hours, so I'm reading the question, it's going to triple. I don't really need to know what the number is. I just need to know what am I going to multiply by. So I'm going to multiply by 3. It will triple. Yeah, that'll be 4,500, but I don't need that because all I need is the starting amount, the base, and the scale. I've got everything I need right here. Should be fairly easy now to throw a function together. Y, oh, I won't use x and y. I'll use the letters here instead. So let's go with p equals. And sometimes students say, do I have to use different letters? Can I use x and y? You can use x and y every time, as long as you make sure you understand which one's the dependent variable and which one is the independent. So the population was dependent upon the time. That makes population dependent. and time independent, so that x is independent and y is always your dependent. So here's my function. P equals my starting amount, my common ratio, which is 3, because it's tripling, to the x over whatever your scale is here. I'm going by 2, so that's your C value. That's the number that goes here. So that'll be a 2. There I have it. There's my exponential function. So I want to know how many will be there after 7 hours. So that's when t is 7. P equals 1500, 3 to the 7 over 2. And then you just throw that into your calculator, which I'll do here now. You don't have to come in advance. So 15, 3 to the exponent. Multiply that by 1500. So after 7 hours, we should have 70,000. And when you're talking about bacteria here, you don't have to be too precise, so we can round these off to whole numbers. Obviously, you can't have a fraction of a bacteria, so we're going to say 70,148. And scientists would probably round that off and just say you'd have approximately 70,000 of these bacteria after that. They're not going to get it. Again, this is just a model of what would happen in, scientifically under ideal conditions. However, when you start putting in external conditions and temperatures and all kinds of things, this will give you a ballpark answer, not an exact answer. All right, so that would be roughly the population of that culture, bacteria culture, after 7 hours. Okay, let's look at a few more examples. So this would be like the chart we've been doing, except everything's listed kind of. I have 2 of them here. So this one here is just a list of numbers. So I look at the numbers and say, well, are these numbers exponential? Well, I look and say, to get from 20 to 100, I had to multiply by 5. Multiply by 5. We're good to go. Well, I would just say this is my beginning. This is my first term. This is my second term. This is my third term. So my exponential function, this one I think I just go with x and y because they don't really have any context. Y would equal my starting amount, my common base, and I'm going up in an increment of 1. So it's just x over 1. There's your function. Okay, here's a chart. There's my x's. They're going up by 2's. I'm multiplying by 4 each time. So my function would be my starting amount, which is 3. My common ratio, or what am I multiplying by? I'm multiplying by 4 every time to the x, but my scale here is 2. So it's not going to be x over 1. It's going to be x over 2. Now, one thing to watch for with these is a real common mistake students make is when we'll pick this one over here. Let's suppose I said, oh, when x is 20, what's the y value? So students will go here and they'll go 3, 4, fill in x is 20. Let's put 20 in for the x. It'll be over 2. And then they'll look here and say, okay, so 20 over 2 is 10. And they'll go 3 times 4 is 12 to the exponent 10. That's not good. You're breaking order of operations if you do that. If you take and multiply this 3 and this 4 together, you're multiplying before you ever deal with that exponent up there. You have to go 4 to the exponent 10, so that's wrong, and then multiply by the 3. So please do not multiply the coefficient by the base and raise it to that exponent. That is a clear violation of order of operations. Okay, so watch for that when you start doing some calculations with these. Percentage is another one you got to watch for. Usually they'll talk about things that are either appreciating. Appreciate just means it's increasing by a certain percentage over time. If something's increasing, you have to make sure you don't, because if you take a number, let's say I took 100, and I told you that was going to increase by 20%. So students say, okay, well that's easy, you just multiply by 0.20, that's 20%, which is right. But the problem is if you take 100 and you multiply by 20%, you get 20. So if you just multiply by 20 by a percentage, you're going to get a number here that is smaller than the starting number. You want your values to be going up, getting bigger and bigger all the time. So if it's increasing by 20%, you'll see here that your base will be 1 plus that. It's like if you go to work at a store and the tax is 15%, let's pick an easy number. Someone's buying something for $100 and you want to put on the HST. Well, there's two ways to do it. You can multiply by 0.15 and say, okay, there's going to be $15 in tax. Add the tax onto here and say your total is now $115. That's what you would owe. Or a more efficient way to do it, all in one, is multiply by 115%. Because when you multiply by 100%, you get back what you started. And then if you wanted another 15% on that, you just take 100 and you multiply by 1.15 instead. That will add the 15% onto this, and you'll arrive at your $115. So for example here, I've got $500. We're going to invest it at a fixed annual rate of 8%. How much will you have after 7 years? So every year you're going to gain 8%. This is what you're starting with. We'll choose those of you that have, which is all of you, that when you've done your foundations 11, you know that there's a formula actually that does anything with money, with compound interest. I'm going to, for the most part, stay away from the money questions just because the work you've done before with compound interest, with that formula, basically takes care of all of this type of calculation for us anyway. But just using this as a starting example, I don't know, I can use X and Y here, it doesn't matter, or I can use A for amount. So how much money am I going to have? Amount will be, what did I start with? 500. What am I multiplying by? What's my base? I'm going to add on 8% every year. So make sure you don't multiply by 0.08. Make sure you multiply by 1.08 to the exponent x, or t for time. And this is every year, so it's just going to be x over 1. Now, depreciation. This is common in when you buy vehicles. So you're buying a vehicle and it's depreciating. Well, if I bought something and it depreciated by, again, we'll pick easy numbers. We'll use money. If I had $100, whatever it was, doesn't matter, and it depreciated, lost value at a rate of 10% per year. Well, that means that the next year you would take what I'm trying to get, say, okay, this is what it's worth now. I'm trying to figure out what is it worth a year later. And what's it worth 2 years later? What's it worth 3 years later? Well, the problem that students say is, okay, all they do is they see a percentage and they multiply the number by 10% without even thinking it through. If I take $100 and multiply by 10%, that's going to tell me how much money I'm going to lose in value off of my $100 object after that year. So I'm going to lose $10. But that doesn't mean that the object's going to be worth $10. The object's going to be worth $90 because I lost 10% of the 100. So what I want to figure out is, well, what could I multiply by to make sure that I get my amount here if I'm depreciating or losing? All right, so if I go to build this function, as we were saying, because we're losing 10%, that means that it's retaining or keeping 90% of its value. Right? So it's going to be worth 90% of what it was the year before because it's losing that 10%. So therefore, in this case, you would subtract the amount. All right, so here would be our situation. So again, you can always turn these into these little charts. I kind of like to do that. So if I go, so this one's talking about buying a new car for $30,500. These cars are known to depreciate, so lose value at a rate of 18% per year. What would be the value of the car after 5 years? So the time in the beginning, so that's always 0. V, what's its value? So the value of the car in the beginning was $30,500. 1 year later, it's going to lose 18% of its value, which means if it loses 18%, it's going to be worth 82% of what it used to be worth. So the next year, you're going to multiply by 0.82 to get the new value of it. So our function will be the value of this car is the starting amount multiplied by the common ratio of 0.82, and to the exponent t, we're going by a scale of 1, so it'd be t over 1. So how much is it worth in 5 years? 30,500 multiplied by 0.82 to the exponent 5. Oops. So my value will be 0.82. Multiply that by 30,500, and it would be worth $11,307.57. So always kind of look at your answer. Does that make sense? So it started out at 30,500. 5 years later, now it's worth this much. Yeah, that seems somewhat reasonable. If this number turned out to be more than this number, that's not reasonable. Something's wrong. Your car isn't going to increase in value as it gets older, unless you keep it long enough to become an antique or something like that. Okay, so that's another situation where we involve percentages. Another common one is, I guess this isn't what I thought it was, but they looked into something called half-life. We'll get to that one next, I guess. This is another bacteria one. There's a little blurb here talking about yeast and how yeast cells, why when they use it in baking, it makes the dough rise. It's because it doubles very quickly through a process called budding. Anyway, the doubling period is, in this example, they're saying is about half an hour for the yeast cells to double. So here's an example of bacteria doubling. So it says bacteria doubles every 3 minutes. If there are 1,000 bacterial, I should say bacteria, initially, how many will there be after a quarter of an hour? Now, one I got to watch for here is units. So right away, I see minutes here and I see hours here. So we got to pick one and do everything in the same unit. Let's suppose we go, again, I like making these little charts. Do you have to make them? No, you do not. If you don't want to, you can just build the function from the words if you like. I'm going to use n for number of bacteria. In the beginning, there were 1,000. So I'm going to go in minutes. So I've chosen minutes as my time frame. 3 minutes, they will double. So I'm going to multiply by 2. So my function is going to be the number of bacteria is the starting amount multiplied by the base of 2 to the exponent t, but because my scale is going by 3, it'll be t over 3. So then it says how many will there be after a quarter of an hour? Well, 0.25 of an hour, right? In 1 hour, there's 60 minutes. So you have to multiply that by 60 and you get 15 minutes. So I'm going to put 15 here, not 0.25. N equals 1,000 to the 15 over 3. 15 over 3 is 5. 2 to the 5 is 32. 32 times 1,000. So that one was easy enough. We could do it in our head. There'd be 32,000 of these bacteria after 15 minutes. Alrighty. All right, so this is the one I was thinking of, half-life. Half-life, this is a common one if you've ever heard the process carbon dating. It's a process that's used in science to determine an age on an artifact or some kind of sometimes they'll find human remains, they want to put a date on them. They can do it using this process called carbon dating. And to do carbon dating, they have to understand something called the half-life. Half-life is basically the amount of time it takes it's usually dealing with radioactive elements. It's the amount of time it takes for a radioactive element to decay to half of its original starting amount. So the example I have here, let me see here. Doesn't show it, but I can see by looking at my data that I started with 10.5 grams. Sorry, I started with 12.6 grams. So 12.6, half of that would be 6.3. I can see that after 4 days, I had 6.1 grams. After 5 days, I had 5.1 grams. So it looks like somewhere between 4 and 5 days would be the half-life of radon, just based on what I see here in the data. So again, so how do you know that? It's because it's how long it takes for a starting amount to decay to half of what you had to start with. Okay, so let's look at an example of a half-life question here. Next slide. So Neptunium 239 has a half-life of 2.3565 days. How much remains of a 10-gram sample after 5 weeks? Okay, as I stated now many times, I like to organize these in a chart. Time, and I'll use M for the mass. In the beginning, I had 10 grams. So I'll just put my units out here. Grams, and we're going to go in days. I do know that after this many days, 2.3565 days, I will have half of what I started with. So that means I'm going to multiply my original amount by a half. So I need to build a function. The mass of Neptunium will be what I started with, my base, which is a half, to the t over my scale. You can see that I'm going by 2.3565. So 5 weeks, we're talking days. So 5 weeks, 5 times 7 is 35 days. That's going to be my t value up here. So the mass will be 10, 1/2 to the 35 over 2.3565. Mass equals, put that into your calculator, 10, 1/2 to the exponent, 2.35, and I end up with 1.953. I'm going to go 3 decimal places, grams. And again, ask yourself, does that make sense? I started with 10 grams. Well, at the very least, I have less, which is what should happen because it's decaying. When we're talking about half-life, it's talking about the radioactive element decaying. And I end up with a number that is smaller. So it should have been half. After that many days, it should have been half. So it would have been at 5. So I'm at 35 days. So yeah, it should be getting smaller and smaller, which gives me a reasonable answer. Now, when it gets into carbon dating, I can't remember if I have an example, but carbon has a half-life of about 5,760 years. So it takes that many years for carbon-12 to decay to half of its original amount, versus this one, which had a half-life of only 2.3565 days. So it decays much quicker than carbon-12. I've got 320 milligrams of iodine 131. It's stored in a laboratory for 40 days. At the end of this period, there's only 10 milligrams of the element remaining. What's the half-life of iodine 131? So this is the first one that's got a bit of a twist to it. It doesn't tell us the half-life. We need to figure it out. So here's what you're going to do. You're going to time mass, started out with 320 milligrams. Now, this is the difference. I don't know how long it takes to end up with the half amount. So my scale up here is unknown. It's okay. Leave it as an unknown. Some people like to just put an X up there, whatever. We'll figure it out here in a second. I know that I'm going to multiply by a half because I'm talking about half-life here. When I go to build the function, it's going to be the mass is equal to the starting amount multiplied by 1/2 to the t over, I don't know what the scale, remember we use C, that's our scale. I'm not sure what the scale is for the half-life to actually work. We need to calculate it. That's why what they'll always do is give you then some other piece of data that you're going to substitute. So what I do know is after 40 days, that's a t, so after 40 days, when t is 40, the mass is 10. They give me this number. So what they're going to do is they're going to give you enough information. So you'll see that we have these three unknowns, m for mass, t for time, and c for your scale along here. Well, c, whatever this number turns out to be, my scale, that's the half-life because it's what it takes to decay to half. So all I got to do now is fill in that other piece of data where it goes. So 40 days would be here, and your 10, so my mass is 10. 320, I'll just kind of color code it here as best I can. So this is going to be 320, that stays the way it is, 1/2. T is going to be 40 days. And then that's going to be over C. There's my unknown. Well, guess where the unknown is? It's up in the exponent. Good news, our last video went through how to solve exponential equations. Equations where the unknown is in the exponent. So that's what we have to do here. We have to solve this equation for the exponent. The way we did that is we tried to get everything to a common base. In this one, I would recommend you divide by that coefficient, both sides first. Now 10 over 320, I'm just going to reduce that. That's 1 over 32. This is 1/2 to the 40 over C. Well, 32 is a power of 2. So how about we change 1 over 32 into 1/2. I know that 32 is 2 to the 5th. Well, if I take 1/2 and put it to the 5th power, 1 to the 5th will give me 1. 2 to the 5 will give me 32. So 1 over 32, you could write it as 1/2 to the 5th. The reason I'm writing it like that is because over here is already 1/2. So 1/2 to the 40 over C. This base and this base are the same. This is how we did our last video or our last unit, last section, we want to call it. The only way this statement could possibly be true is if this exponent equaled this. 5 would have to equal 40 over C. 5 times C would have to equal 40. Divide both sides by 5. So I now know that my scale, right, I just found the C value. The C value coincides with what your scale is going by here in the beginning. That's your C value, this one, which was also going to coincide with then what it took to get half. So the half-life of iodine, 131, would have to be 8 days. Okay, so there's an example where you solve for the half-life. The issue that we run into right now is that these questions have to be set up in what I would consider to be cookie cutter questions. They've got to be perfect and work out so that the number here will turn out to be a power of 2 if this is a 1/2 over here. Scientifically, that's not what happens. These numbers aren't always going to match up perfectly like that. So eventually, we need to identify a strategy that will let us do this when these bases are not numbers we can easily change to the same value. And we will get to that. That'll be our next video after this one. How do I deal with exponential situations where the bases can't be changed to the same thing? But for now, we won't have to worry about that. All right, here's one talking about medication. So it says doctors prescribe medicine. They must consider how much the drug's effectiveness will decrease as time passes. This is often how they'll set up like an intravenous to a patient. So they'll have it set up to constantly maintain a certain level. it says here, suppose that a drug is only 95% as effective as the previous hour. At some point, the patient's not going to be receiving enough medicine and must be given another dosage. So if the initial dose was 250 milligrams and the drug was administered 3 hours ago, how long will it take for that initial dose to reach a dangerously low level of 52 milligrams? So this is some situation where a patient is being administered some certain medication and they need to have it at a certain level in their body, or else the body's going to start running into problems. So they're telling us that if it gets to 52 milligrams, that's going to be dangerously low. So we're going to try and figure out how long is it going to take for the drug to get to that level. So let's start with time. And let's go with M, I guess, for mass, or some people use whatever letter you want to use, D for dosage, whatever. In the beginning, they received 250 milligrams. The drug was administered 3 hours ago. How long will it take to reach 52 milligrams? So this one, oh yeah, so here's my 95%. So after 1 hour, that drug is going to be 95% as effective as what was there. So that means if you have 250 milligrams, you're going to be only having 95% of that remaining in 1 hour. So my function, so the mass remaining of the dosage would be 250, 95% remaining, and my scale is 1, so just to the exponent t. They want us to figure out how long it's going to take for that to get to 52 milligrams. So 52 milligrams equals 250.95 to the exponent t. 52 over 250. So this is going to get to the situation I was just alluding to. 52 over 250 equals 0.95 to the t. So this is a more realistic example. So watch what happened here. So when I take 52 and I divide by 250, I get 0.208. Well, that's not that nice numbers like the last one where everything was these beautiful powers of 2. So essentially what you have to do at this point is figure out 0.9, because I need the base to be 0.95. So 0.95 raised to what exponent will give me 0.208, because I want the bases to be the same. We will eventually learn a way to just tap some buttons on our calculator and it'll tell us the exact answer. You don't know how to do that yet. So at this point, the only thing you can do, I always tell students, is play the Price is Right guessing game. Just trial and error until you find something that works. So for example, the Price is Right game, I don't know if you've ever seen the higher or lower one where they got to try and guess the price. So they'll say a price and the host will say higher or lower. You're going to make a guess. You're going to go 0.95, pick 10. I was like, kind of start with 10. So 0.95 to the 10 and see what you get. 0.95 to the exponent 10, and I get 0.598. So I would say, well, that's too big, right? I only want it to be this much. So let's make the exponent bigger. Let's go to the 0.95 to the exponent 20. So I went 20. I ended up with 0.358. It's getting closer, right? I'm trying to get it to equal that. Not quite yet. Let's try 30. 0.95 to the 30. That's getting really close. So 0.95 to the 30. 0.95 to the exponent 30, I'm at 0.214. Well, that's a pretty good approximation for that. And you can maybe say, well, let's try 32, see what that does. So 0.95 to the exponent 32. And I'm at 0.193, so I don't want that. Let's go 0.95 to the 31. That's at 0.204. So 0.95 to the 31 is 0.204. So it's somewhere between 30 and 31. We're talking, what do we have here? Hours, I believe. Yeah, so we're talking about hours. So it's approximately, that's what this little equal sign that's swirled like that means, approximately. It's going to take approximately 30 hours for that drug to decay to an amount where it's only 52 milligrams in their body. I don't spend too much time worrying about this kind of thing because I know that in the next section, I'm going to show you a way to mathematically calculate this out. So this whole trial and error, Price is Right guessing game is not really something you're going to have to do by next week. But if we run into it for now, that's our only option because we don't have the skill set yet to deal with that. You'll find, I believe, in the textbook in particular, they set up the question so you don't have to worry too much about doing this. But I wanted you to see kind of the theory behind what happens in real science. All right, a couple more quick questions, and then we'll give you some practice to try in your textbook and get ourselves ready to move on to our last section on logarithms. So it says your baby brother has an ear infection. The doctor said that there are probably 50 million bacteria in his left ear. The penicillin the doctor prescribed will kill 7% of the bacteria every hour. How many bacteria will be in your brother's ear in 5 days? That's a gruesome question, but scientific nonetheless. So time in the beginning, I'll use B for bacteria. He had 50 million bacteria. I know that every 1 hour, so in 1 hour, now you're going to kill 7%. This number is how many bacteria are there. So if you kill 7%, that means there's still going to be 93% remaining. So your common ratio to get the amount of bacteria in that ear 1 hour later would be to multiply by 0.93, not 0.07, because that would mean that there's only 7% left. There's going to be 93% left. Here's our function. The bacteria in the ear would equal the starting amount, common ratio, 0.93. My scale is 1, so it's just to the t. This is hours. Again, you do have to pay close attention to units, so this is hours. 5 days, well, every day is 24 hours, so 5 times 24 would be 120 hours. So it's going to be 50 million, 0.93 to the exponent 120, and this will give us an estimate for the bacteria. And again, you can round this off to whole. You don't have to be too precise. So it's going to be 50 million to the 0.93 to the exponent 120, and I get around 80 to 159 approximately. Put a dot over, that's another way to put approximately. Just put a dot over your equal sign or the swirly equal sign. They both mean the same thing. 80 to 159. And again, that's probably way more precise than you would need to be. A doctor would say, oh, there'll be approximately 8,000 bacteria based on our calculations. That one's pretty straightforward. Another half-life one. The original weight of a certain radioactive substance is 100 grams. After 2 hours, it decays to 12.5 grams. Find the half-life of this substance. Well, let's set it up the way we did the last one. We went time, m for mass. We said in the beginning, there was 100 grams. We didn't know what the scale was in order to end up with our half-life, so we're going to multiply by a half. So our function was going to be the mass is 100 to the 1/2 raised to the exponent t over c. They told us this is that other piece of data they'll give you. Then you use that to figure out the c value. So they told me the mass is going to be 12.5 grams. After 2 hours, Make sure you don't mix up the t and the c, right? This is the time that has elapsed. C is your scale up here. 0.125 is equal to 1/2 to the exponent 2 over c. Now, when this is a decimal, some of you might have the option on your calculator to switch decimals to fractions. I'm pretty sure that 0.125 is like 1/8 or something. Yeah, it is. So 0.125, you could do it this way. So what's that as a fraction? 125 over 1,000, because you get 3 decimal places. That reduces to 1/8. So this would be an example of what I meant earlier by a cookie cutter question, because this is going to work perfect. This is a power of 2. This is a power of 2 over here. It's going to work out nicely for us. Which, as I said, in your textbook, at this point, most things will, until we learn what are called logarithms. This will be 1/2 cubed. 2 cubed is 8. This is 1/2 to the 2 over c. This has to equal this, because the bases are now the same. So 3c is equal to 2. So c is equal to 2/3. Let's see what we're talking about here. For units, we're talking about, this is an hour. So everything I've been working with here is an hour. So it takes 2/3 of an hour. That will be the half-life of this radioactive substance. So half-life is 2/3 of an hour. All right, so that is a run through of how to create exponential functions and then use them to answer questions about a particular situation. Oh, I do want to do one like this. Sorry, I forgot I had this. This is another way they'll present these questions. It's given us a half-life, so it's talking about nickel. Nickel 65. So let's build our little chart. So time and mass in the beginning. The difference here is they don't tell us the starting amount. So I'm just going to call it mass, I'll put subscript O, original mass. I do know that the half-life, so in 2.5 hours, I will have half of what I started with. So how do you know that? Because it says the half-life is 2.5 hours. So when you go to build your function, you're going to go mass equals the original mass. Some people like to put an A there or an X or whatever. I like using that symbol. So original mass, half-life, to the exponent t over 2.5. Now, our goal this time is to figure out how long it takes for an original sample, this amount, to decay so that there's this much left of the original mass. Now you got to watch the way these are worded. Sometimes it'll say how long will it take for this much to decay. Sometimes it will say how long it will take for this fraction to remain. Or sometimes it'll give you a percentage here. Well, the dilemma students run in and say, well, I don't know the starting amount. Here's the good news. You don't need to know it. You know what some students will actually do? They'll just pick a number and they'll put like 100 here, or they'll put 1, or they'll put 10. They'll pick some easy number and just fill it in here. And you can do that, but you don't have to. You'll see why in a second. Because here's what they said. You're going to decay to 1 over 1,024 of the original mass. So that means you will have 1 over 1,024 of this amount, whatever it was, doesn't matter what it was, equals that starting amount, 1/2 to the t over 2.5. Well, here's why you don't need to know the starting amount. Notice you're multiplying both sides by the same number, whatever that number was, doesn't matter what it was. Again, you could have put an A, you could have put a 10, you could have put a 50. It's going to be here and here. Well, because you're multiplying both sides by the same thing, you would just divide by it. That's gone. That's gone. When those two divide each other out, you're down to 1 over 1,024. equals 1/2 to the t over 2.5. Good news. 1024 is a power of 2. Now you may say, oh, how do I know that? Well, it comes with experience, but if you're not sure, there we go. Sorry. There's a button I hit that messes things up on me. Get rid of that. Yeah, so 1024, if you're not sure, just use your calculator and, as I said, play some Prices Right trial and error. Just try and find numbers. You should have some kind of benchmarks. Like you should know by now that 2 to the 5th is 32. So you know that it's bigger than that. Let's try 2 to the 10th power. 2 to the exponent 10. Look at that. First one I tried worked. 2 to the 10 is 1024. Now, I did not know that off the top of my head, but I knew it was a power of 2 just because I've seen it enough. I just had to figure out which one it was. So it happened the first one I tried was the correct one. So this 1024, you're going to write it as 1 over. Now, again, you can put 1 over 2 to the 10th, but it's just as easy to put 1/2 in brackets to the 10th because 1 to the 10th is your 1, 2 to the 10th is your 1024. And the reason I would do that is because the other side is already base 1/2. So now I have 1/2 to an exponent equals 1/2 to an exponent. That can only possibly work if this is true. The exponents have to be the same. And now I solve. So 10.5 or 10 multiplied by 2.5, 25 equals t. So what does that mean? Go read my question again, see what t actually is. So t is the time it would take for us to start out with some amount, I don't know what it was, and decay in such a way that there's 1 over 1024th remaining. So it would take, we're in hours, so it would take 25 hours for this to happen. You should always put units on these questions and answer their question. There's the answer to the question. It would take 25 hours. Doesn't have to be a fancy sentence or anything, but there should certainly be units indicated on the answers. There we go. Here's some practice questions you can use in your textbook. I'm not sure if we'll do another assignment this week. We may just jump right to logarithms in our next video. And as you know, there's only another few weeks left in the course, so we're kind of picking and choosing which things we're going to do and what we're going to get assignments on. But this set of questions, there's not that many in your book. There's only the 4 of them, but that would be enough if you look at those to give you an idea of how you're doing with creating these exponential functions and equations. All right, thank you for watching.